Okay, so I guess it's happening. All right, everybody. I'm really happy to introduce Zihao Zhang, who is at Oxford and currently coming to us from China. So I'm real happy to have this global seminar this semester, and we're gonna hear him talk about deep learning for market order data. So Zihao, I'm really excited to sort of see how you approach market microstructure, not so much from the perspective of limit orders, but by observing the market orders and the trades in the market, and specifically taking this deep learning angle, which I know many people in our audience are excited about. So welcome to the seminar, and look forward to your talk.
Thanks, Sasha. Hi, I'm Zihao. And thanks, Peter, Sasha, and Rizal for inviting me to the seminar, and thanks all for your time today. So I'm a postdoc at Oxford Institute, and also I'm part of the machine learning research group here. At the moment, I'm in China and working at a hedge fund that's doing high frequency trading. So in this seminar, I'm going to present our recent work that applies deep learning model to market by order data. And this is a joint work with Brian Lim and Stefan Zoran. So here's today's agenda. So I will start with a very brief introduction. So just and describe the market microstructure data, including the limit order book and the market by order data, or the MBO data. Then I will introduce our deep learning model and discuss the network architectures. So we designed some specific architecture for this type of data. After that, I will present our results and show you some interesting results. At the end, there'll be a summary. So I will conclude the talk and discuss some interesting future work. So here's the overall the agenda. And let's go to the introduction. So in this paper, we study the market by order data. The market by order data is essentially just a sequence of messages that describe actions of individual traders, because those are high frequency microstructure data. So those are kind of instructions given by different traders. And it is arguably one of the most granular sources of information. So you have more updates, so you have more events for the MBO data compared to the limit order book data, because the limit order book data are actually derived from such messages, so derived from the MBO data. But the MBO data is currently kind of largely neglected by the current literature. So one of our motivations is actually to fill in this gap. So if you look at the high frequency data, if you look at the paper, most of the paper are doing modeling on the limit order book data. There's I think that at the time of writing this paper, we haven't found any literature on this. So that's kind of our motivation to fill in this gap. And we apply deep learning model like the LSTM and the attention mechanism to model the dynamics of market by order data. And we use those models for predictions. And I think to the best of our knowledge, this is the first predictive model using the MBO data for forecasting the high frequency movement. And we see that MBO data provides an orthogonal source of information, so kind of additional information to limit order book, which helps to expand the universe of alpha discovery. So we think there'll be some interesting things, so some interesting features that people can derive from the market by order data. And those information will be additional to the limit order book, and those information will be helpful for funding alpha or funding or be helpful for predicting returns and etc. So that's the overall that's the goal of this work. Then let's take a closer look at limit order book and the market by order data, because they're highly correlated. So this animation shows the evolution of the limit order book. So in case if you haven't, if if you don't know the limit order book, so the limit order book is simply a record of all outstanding limit orders for an instrument at a given time point. So if you have seen some like stock charts or stock price, so you see the candlestick charts, etc., but those are like the low frequency data. So you get a high-low, open close price for a specific instrument. But if you zoom into that chart, the price of a stock or security is actually not a single value, but multivariate time series. And that is actually the limit order book. So you can see the limit order book of a given instrument. This one is actually a Lloyd. I think this is a Lloyd from the last year. And you see limit order book is sorted into different price levels. And those price levels are actually based on the submitted orders. So because when you submit a limit order, you get option. So you can specify the price and the quantity of your interest. And those orders will stay in the book until they be matched. And you see there's two sides here, the ask side and the bid side. So the ask side shows all the selling orders and the bid side presents all the buying orders. And you see each price level here. So each price level, each bar here consists of many small orders because those orders are submitted by different traders. And overall, we have those amount of quantity for each price level. And the order book get updated when there's a new message coming in. So this message can add a new position, so add a new orders or cancel an existing order, or maybe just update the existing order. And when the message comes in, we get a new update. And such individual messages are actually just the market by order data, and it displays traders' action. So we can restructure the limit order book step by step. And this animation shows how the order book evolves by incorporating incoming market by order messages. So if you play it again, you can see how it get updated. So we get an update of the limit order book whenever there's a change. So this can be like addition of the orders or a cancellation or etc. And let's take a look at those messages. So as I mentioned, those are just individual messages from the various traders. So if you look at the table here, we have the timestamp. So you see the timestamp here. Those are not regular time intervals because those are the moments that message is being sent out. And we have the ID. So those ID identify the traders, but they are anonymous. So you won't be able to know who's doing this trade, and we have the type. So the order type says if it's a limit order or market order, and then we have the side, which basically tells if it's on the ask side or the bid side, and action like cancellation, addition of an order, or just update of an order, and we have the price and the size as well. So you see we have those type of messages, and those messages comes in, and the limit order book get updated. So the limit order actually is the derived data, and the limit order shows the overall demand and supply relationship for a specific instrument. But the raw data, the underlying data, is the market by order data. So which are just the kind of placement and cancellation message. And our interest is to see if we can just use those type of messages to make predictions, and see if those type of messages will provide additional information. So that's a focus. And now let's just look at how the MBO data updates and limit order book. I'm gonna present 4 different scenarios, and the first one is a placement. So it's an addition of an order, and you can see on the left side here we have a limit order. We have a snapshot of limit order book at time t, and there's a new message coming in. So this new message is essentially market by order data. So from this ID, from this person, on the ask side, the type specifies which side of the book. The type specifies if it's a limit order or market order, and we have the side. specifying it's on the ask side, and the action. So we're adding a order here. So you see at time t, there's nothing here, but this message says we're going to add some orders to the to this price level. So the 70.04 with this amount of shares, so 7,580 shares. So this is a message. This is a typical message of the MBO data, and we got a new update. So those time intervals are not in regular intervals. We often refer this as the tick time. So it represents the change of the limit order book. And similarly, we have the cancellation. Again, from this person, we have an existing order standing in the limit order book, and we're gonna cancel the entire position. And we have again, we have a new update of the order book. And we can also do like partial cancellation or update. So for example, in this case, we have an order of this amount, but we're going to reduce our size to half of what we had before. And you see the action. You see the action will be different. And the last case is an aggressive order. So basically, basically this order says we're gonna cross the spread. So the spread is a difference between the first ask price and the first bid price. So we're gonna cross the spread, and we're gonna make a trade. So this is the last example. So in this case, we're gonna buy this amount of share at this price level, and you see this amount of order being matched. So it's gone. And so those are the 4 different scenarios. Now let's move on to the deep learning model. As I mentioned, the current literature focus on the limit order book, but just to remind you our motivation, we like to use those message string from market order data and model them directly and make predictions. So the MBO data is lower dimensional than the limit order book. So we have less features, but it's a bit difficult to learn the structure because those are individual message and they do not explicitly show the overall demand and supply relationship. But the limit order book does that. So however, the results indicate that those type of message provide us with additional information compared to the limit order book. So on top of the limit order book, I mean. And just a little bit recap on what we did before. So we started with the limit order book, I think 2 years ago. So what we did is we collect the limit order book data. So at a time point, at any given time point of t, we take past few events like 50 updates or etc. We can form that as an image, so it's kind of a space-time picture. So on the y-axis, we have different features. So essentially just different levels of the order book, and on the x-axis we have the time. So this form like 2D matrix. So this is an input at time t, and we can give this input to a neural network, and we can predict the market movement. So this is the typical structure of the model, and this is actually one of our previous work. So we use the limit order book data to make predictions. So it's just a quick recap showing how to use limit order book to make predictions, and later on we're going to compare it with the market order data. And you see we have an input, which is a limit order book image, and this can go through a series layers of convolutional layers, or inception module, or ResNet, etc. And we output the resulting features from the convolutional layer to the recurrent neural layers. So the recurrent neural layer, the LSTM here, can learn the structure. So additional dependencies from the CNN features, and as the last layer, we can output the predictions. So in this case, it's a simple like classification setup where we have the up, neutral, and down. Those labels can be decided by using returns with a threshold. So if the return is above a certain threshold, we see the market going to go up, or on the vice versa, the market going to go down. So this is a typical structure that network architecture that we use for making predictions from limit order book. And in terms of the market by order data, what we did is to replace the first two components. So we're no longer using the order book data, but we use a message from the MBO data, and we're going to replace the convolutional layers because the message is a lower dimensional than the order book, less structured data. And here's the typical example. So we have the input MBO data. Those are messages from individual traders seeing what they're going to do, like buy this amount of shares or sell, or maybe just updating existing message. Those just a message that are displayed before, and we're going to put those message directly to an LSTM layer or attention layer. At the end, we're still going to make a classification. So it's still a classification problem. So we're going to make the predictions, so predicting market movement. Then I can just briefly introduce the attention mechanism as I put here. So the LSTM is quite straightforward, and also we experimented with the attention mechanism just in case if you are not familiar with the attention mechanism. So for given input of this length of capital T, we use the attention mechanism. So the attention mechanism typically have an encoder and decoder structure. The encoder can be just an LSTM, and the encoder kind of steps through the input times to extract meaningful features. So you can think of those x1, x2, xt as the limit order book, like at each time point. And the encoder steps through those time points to extract the features from the order book or from the market by order data. So you can think each point is a message, and we take past a few messages and form an input, and the encoder will first extract the information from those time points, and the encoder will summarize those information to a hidden state, and this is a context vector. So the context vector summarizes the information from each hidden state. And finally, we have the decoder here. So the decoder will generate the prediction. So in general, the attention mechanism is used for sequence-to-sequence learning, where we have the multi-input and output. But here we are just using it for a single point prediction. In one of our paper we used the attention for building multi-horizon predictions. But in this case, it's a single point estimation. And this is just a simple illustration of the attention mechanism. And now let's present you with some results.
May I ask you a quick question?
Yeah.
Could you back to the previous slide, just about, I'm trying to understand the data as it's coming into the model. So if you have a buy 8560 at 704, and let's say it's a limit order, does the model know what the best bid and the best ask is, or is there no memory of that?
Oh yeah, it doesn't. It won't know specifically, but through the normalization, it will count. So essentially through the normalization, it will know if it's a ask order or a bid order, because we normalize the price against the mid price. So if this price is above the mid price, then the normalized price will be above 1. So basically,
I see. So this you do a little transformation of the raw data into it's relative to mid at this input stage.
Yeah, I think if I show you the original message, so the original message looks like this. So in the input, we won't have the ID. But we have the side action, price, and the size. We don't have the type as well, because more than 95% of those messages are limit orders, market orders. It's only account for a few percentage of the overall order flow. So mainly the side action and price and the size. We do a little bit, we do the transformation here. So mainly the price and the size, because we train a model with a group of assets. So we have to normalize them to a similar scale.
Okay, so I just wanted to make sure that at every timestamp we know the best bid and best ask, and it's normalized with respect to that. Makes sense?
Yeah. So let me go to the results bit. Yeah, so let me present you with some results. Just to introduce a setup. So we have a classification setup of predicting market movement. So 3 labels, +1, 0, -1. So the market is going up, staying stationary, and -1. And we have in total we have 12 months of data. So that's about like 134 million samples. We split them into train, validation, and test site. So the first 6 months are the training site, and we select 5 instruments. So the Lloyd's, bucket, Haskell, BT, and waterfall. The next 3 months are the validation site, and the last 3 months are the out of sample data, the testing site. And we make predictions at different prediction horizons. So basically 20, 50, 100 ticks ahead. So in clock time, that's kind of like 5, 10, or 30 seconds ahead. So in clock time. And here's the results for the prediction horizon at 20 ticks ahead, and we tested on different models. So you see the LM is just a simple linear model, and multi-layer perceptions, LSTM, and attention model. This MBO indicates this model is trained using the MBO data, and the LOB here means the model is trained with limit order book data. So overall, you can see the model trained with limit order book data are still better. The results from MBO data are comparable, but not as good as the order book data. This is not very surprising because the order book data shows the overall demand supply relationship, because those are aggregated data from different orders. The MBO data are just individual messages. So they display individual actions, but they do not show the overall demand and supply relationship. But what interesting is you can see we still get some decent results from just directly modeling those raw messages. However, the pure MBO data cannot outperform the limit order book. So if you look at the F1 score here, the data because it's a classification problem, the labels are slightly unbalanced. So you need to focus on the F1 score as a mean evaluation matrix. But the interesting thing is if we look at the correlation between the predictive signals, so you can see the predictive signal from the MBO data are less correlated with the limit order book, with the model trained from limit order book, because if you look at the LSTM that are trained from order book, you see that the signals are highly correlated, but they're less correlated with the signals from the MBO data. So that means if we can combine those 2 signals, we can benefit from the diversification, and also it means that we actually extract something from the MBO data that is not captured by the order book. So a combination of the 2 signals from those 2 types of data can benefit from the diversification, and also kind of reduce the signal variance, and we can get better predictive signals. And to verify that, we include an ensemble model in our experiments. This ensemble model is very simple. It just equal weighted average of predictive signal from the MBO data and from the market by order data. And you can see this ensemble model gives the best performance. and this is a result where we combine two signals. So this, to some extent, indicates the potential benefits of using the of incorporating the MBO data into predictions, because we just directly use the MBO data. You can do some transformation of the MBO data, and you can do a little bit of feature engineering as well. And we think that's gonna be helpful as well. So this table shows the results at the prediction horizon of 20 ticks ahead, and we have the results for 50 and 100 ticks ahead, and you see similar behaviors here. So
I have a few implementation questions in the chat room. Would this be a good time to ask them, or?
Yeah. Mm-hmm. Yeah.
Okay, yeah. So I have one question from Peter de Krem is, does this normalization work with multiple securities that are potentially co-integrated, or do you do this one security at a time, or is it the same?
Yeah, we train a single model by using all the instruments. That's in general helpful for generalization, because there's kind of a little bit stochastic there. I mean, so in general, we find it helpful to train a big model with all the instruments, and you can fine tune. And after that, you can fine tune the model for each instrument. Maybe fix the convolutional block, or fix the first few layers, and just fine tune the last layer, and that's gonna give. Sometimes that's gonna give an improvement of the results. Yeah. Mm-hmm.
I see. So you throw everything, all the stocks together into the neural. Okay.
Yeah.
Another question I have from David Fitzpatrick is this MBO data bought from a specific exchange, or is it multiple?
We're sponsored by the Man Group, so we have access to Tom's router. So those data comes from Tom's router, and those data from the London Stock Exchange. Yeah. Mm-hmm.
Okay, so it's a single exchange, and it's London Stock Exchange. Okay, great.
Yeah. Mm-hmm. Yeah.
And I also have a question about how you define. So David Mandel is asking, how do you define a tick up or tick down? Is it exactly the mid price moves by more than X, or by, and is X one tick, or is it multiple ticks?
Yeah, I think there's a few ways to define the labels here. So I mean, the first one, probably the most straightforward one, is you just take the return. You just take the return of future price, like the PT plus K minus PT, and divide it by the PT. That's return. You can use that. That's one way. And I saw the other ways of defining returns, like you can take the average of the price. You can do, it's kind of a little bit like a small thing, and you take the return of that, and also you can specify a path. So in this path, if you find a point that give you the return higher than the threshold, then you can see you get an update. So in this paper, we take the second approach. So it's average of the future price, and take that as a price, and compare that with the current time point. That's what we did for this one. Yeah. Mm-hmm.
Okay. All right. In order not to interrupt the flow too much, I'll ask you this one last one and keep the rest for the end. Someone is asking, Patrick Dote is asking, why focus on F1 when ultimately PNL is the measure of success, and 61% could have a better skew than 68?
Yeah, I mean, you can definitely focus on the PNL. That's
it's just
I mean, that's good. That's a good point. Yeah. I think the problem is, I mean, sometimes just see when you transfer the predictive signal to the positions, you can there's various ways of doing that. So I mean, you can just use a raw signal and treat that as a positions. That's fine. But sometimes people probably gonna define some rules like when the probability from the softmax is higher than a certain threshold, then only at that time point you enter the position. So that's a little bit different here, but yeah, I mean we can check that PNL. That's absolutely fine. That's a very good point. Yeah. Yeah.
Okay, I have a few more questions, but I'll keep them for the end of your talk. So
okay, yeah, thanks. Yeah. So I think we're just gonna summarize this paper and be the end of the talk. So in this paper, we propose to model the message from the MBO data directly instead of using the commonly used order book data. Since one of the motivation is really to introduce this type of data because it has been neglected by the literature, and we tested on deep learning models, including the LSTM and attention mechanism, and we expect those architectures can extract some features from the market by order data and use those type of features for predictions. So the results indicate the MBO data gives different results, but still cannot outperform the limit order book data. But a combination of both signals give the best results. So in the future, we're thinking we can probably do some feature engineering things, or a little bit of research on that side, and see if we can extract more information from the market by order data. And that's all from me. And thanks very much. And I'm happy to answer any question on this one. Yeah.
all right. So yeah, I do have a few more questions in the chat. So please, for the audience, if you have some questions, that would be a great time to ask them. So I've got Peter de Krem asking, what was the autocorrelation between market moves? Did you find that? Did you measure that, or is that something?
No, we haven't measured that, but we can have a look after. Yeah.
Okay. So Philippe Perumal is asking, if we assume that some trades are from so-called noise traders, can we filter out these trades and build a model only from those trades that convey more information in alpha? Thanks.
I mean, yeah, I mean, I think that's possible, because when you refer to the noise trade, I assume you mean the orders that are being added and cancelled, and in general, I think the orders in the deep side, in the deep level of the order book, have been constantly cancelled, and a large percent of them are just being cancelled. So if you so after the normalization, you see the distance from the price you submitted against the mid price, and if the price is above certain levels, and you can probably treat that as a noise trade and cancel them.
Yeah, I think in the literature, often noise trader just means an uninformed, essentially bad trader who doesn't know, who has no predictability. So I think the question is trying to see, can you filter, does your model maybe filter out in any way these trades? But it doesn't seem like it's explicitly done.
I don't think it will explicitly do that. Yeah.
Okay, now we have someone who seems to, Karen Lin, who seems to have some experience with neural networks, who asks, what's the motivation for first making a limit order picture using CNN layer and not directly putting time series data into LSTM?
Yeah, it's the it's due to the property of the limit order book. So the limit order book are sorted into different levels. I mean, you can put the limit order book directly into the LSTM layers, but you can treat them as a spatial, but there's kind of spatial structure that can be explored by the CNN layers, and that's what we experimented before. So because essentially you have different layers, each layer has a price and level, and they're ordered. And if you use a CNN, and you can first extract the information from the price, and because essentially the CNN is kind of like a filter. It's kind of like a little bit like a smoothing filter. You can first use a CNN layer to extract information from each price level, summarize the information from price and the volume, and you can move the window at each price level. Then you can use several CNN layers and combine the information, do another layer of filtering, and at the end we find it would be helpful for predictions. And if you're interested in this, in why we are using the CNN for order book data, and I think probably it's easier if you look at our previous paper, the deep LOB one. We do a detailed explanation of why we are doing that. Yeah.
Okay, thanks. We have so we have a question by Chen Benar who asks, any insights on why you used the learning network architecture you described? So maybe we could look at the slide where you show the architecture and
this one.
Yeah. So I guess Chen Benar is asking a little bit about insights or of why this specific structure is useful, or is
yeah. So I think it's kind of related to the type of the data. So those type of message. So in general, I mean so we can use a multi-linear perception, multi-layer perceptions, but the problem of the multi-linear perception is we need to flatten the input, and that would distort the time. The time flows a little bit because you essentially treat each feature independently, and the LSTM is better because LSTM layer shares parameters to some extent, and the LSTM kind of steps the information from the past events and kind of summarize that to a hidden state, and propagate that information from the past to the current time point. So the LSTM, the focus, and the reason of having this attention mechanism is because the LSTM layer only takes information from the last hidden state to make predictions, but we want to see if by using information at each hidden state, and we just want to see if the past events, see whether the past events can contribute to the prediction. So that's why we also exploited with the attention mechanism. But I think the benefits from the attention mechanism is limited, just because it's due to the property of the financial time series. So that to some extent, the most recent time points summarize the most information for the time series. So the benefits of using attention mechanism is not that significant compared to a simple LSTM layer. Yeah.
And I guess because of the normalization you're doing, you always know where you are relative to the mid price. So that I think in a way is a form of attention, I guess. So now we have Domenico Spoto, who asks, how many hyperparameters are you tuning in the CNN and LSTM models?
Oh yeah, that's a good question. I can't really remember. It has been a while, but that's not a I think in the paper we specify all the hyperparameters. There's a few, but not that many. I think in the paper we put a detailed description of what kind of hyperparameters we tune for the model. Yeah. I just can't remember at the moment. Yeah. Sorry about that.
But in terms of an order of magnitude, I guess if you're taking 20 inputs, it's in the maybe 100 or 2, but not 1,000 or 2. Would that be right?
I think we tune the number of layers and number of neurons at each layer, and the learning rate and the batch size, and I think that's it. Yeah, that's we didn't tune a lot of parameter for this one. Yeah.
So yeah, I mean that's often a criticism of neural network methods, is the amount of parameters seems to be quite large.
Yeah.
But you think they're not that large?
I think probably just we often use this type of model, so we can't know what kind of combination of parameter gonna work out or not. If it doesn't work out, then it probably just means it's not suitable for this type of data. So we didn't train a lot of we did train a lot of model in previous works, but in this one not that much. Yeah. But the network often have this problem. Yeah, you have a large space for tuning the hyperparameter. Yeah.
Okay. I guess so. Now we have a question by Jae-myung Kim, who asks, how do you define the success case? Does it include bid-ask spread cost, i.e. success even when taking liquidity into account? So I guess that in the question of your response, you take the change in the returns, and you define these up, down, middle states. But have you ever, or have you considered using the bid-ask spread as a criterion in there?
No, we haven't, but that's a good point. I mean, you can look at that. I think it's just because of our motivation is to demonstrate how can we use the MBO messages. So we haven't looked into those details and those type of metrics, but I think it's always good to look at that. Yeah, but we haven't done that yet.
Yeah, I mean, I think that there's something. Maybe I'll put in my question here, is that you've done this for multiple horizons, right, and different thresholds. So I wonder, do you have some insight on what application you have in mind? In terms of, are we talking about high frequency trading or order execution, or do you have some kind of insight into for what application is this the most useful?
Yeah, I think as you said, trade execution is one of them, and probably some market making type of strategies. Or you can downsample the data a little bit to the probably to like 3-second intervals or even 1-second intervals, and you can build some strategy, and being a liquidity taker, then you can because if for the raw limit order book data, we got we got too many updates, and it's really difficult to cross the spread to make a trade. So so it's usually for the market making or trade execution. So you can assume you're doing trade on one side of the book. And if you want to cross the spread, and you probably need to downsample the data a little bit.
Okay, so we have a question by Rainer Hoft, and the question is, when modeling the limit order book, do you include information about the individual order sizes, or do you just aggregate the total size at each price level? Which I guess it's related to, MOB versus LOB. Like when you talk about the limit order book, are we aggregating, or are we just Is the
Yeah,
information each price level there?
yeah, for the limit order book, it's the aggregated price and the volume, aggregates the volume. Yeah, so for the order book, it's overall order size for each price level, not individual orders. Yeah.
Okay.
But for the MBO data, those are the individual positions, individual orders. Yeah.
Yeah. So that's probably where you get some of the additional alpha, I guess, is from the you know, I guess one order of size 10,000 is different than 10 orders of size 1,000.
Yeah. So actually, if you do some, so you can actually, because we have the ID, those are anonymous IDs, but those IDs won't change during a day. So from the MBO data, you can actually you can trace back and look at the behavior of each individual order, see how they respond, like if they cancel their positions or if they're adding position to their existing order. So that's something you can get from the order book, from the MBO data, but those type of information are not available from the limit order book data. So there's some additional information there, but so we think with a proper feature engineering things, we can get something out from there. Yeah. Yeah.
Okay. I have a question from Umu Chetin, who asks, in contrast to semi-cancellations, does your model include updates in the price of a particular limit order, keeping the size unchanged? So I guess an order that's at the best bid that's sort of modified to move up with the price, for example.
Again, that will be just that we treat them as a new update. Yeah, so you have new message that size won't move, just the price getting updated. Yeah, that can happen. Yeah.
Okay. Well, I think that's it in terms of questions on our end. Zihao, thank you very much for being sort of concise, but at the same time, really presenting some interesting material, you know, that combines microstructure and neural networks in a way that's insightful. So, so thank you very much. To our audience, we'll thank you for the great questions, and I look forward to seeing you next month for our next seminar. So thank you very much, Zihao, and good morning.
Yeah. Yeah. Thanks.